So 4.4 is all about the properties of logs, and our objectives or sort of goals or things we want to walk away from this lesson are as follows. Hopefully by the end of this video, you can use properties to evaluate logs without a calculator, use properties to do this thing called expansion of logarithmic expressions, use properties to do the exact opposite, which is condensing logarithmic expressions, and using this neat change of base formula to sort of evaluate logs that are harder to do on a calculator. Now, overall, let's recap an idea. In its simplistic form, the idea of a log is it's just an exponent. So we've already talked about properties of exponents. It sort of stands to reason that there must be some relationship between properties of exponents and properties of logs, and indeed that is the case. So let's recap or recall the properties of exponents. So there were 5 properties. I'm only going to focus on the main 3 of them. We have the product property of exponents, which says if you multiply like bases, you add the exponents. We have the quotient property that says if you divide like bases, you subtract the exponents. And we have the power property, which says if you have an exponential expression and you raise it to another exponential expression, you multiply the exponents. What I sort of want to highlight is these properties of exponents sort of bridge or connect two mathematical operations together. The product property, it connects multiplication with addition of exponents. The quotient property, it connects division with subtraction of exponents. Power property, it connects exponents, exponentiation, with multiplying. That connection, multiplying is with adding, dividing is with subtracting, raising an exponent is related to multiplying. Not surprisingly, when we look at the properties of logs, they have the same relationship. So this will be what we want to focus on today. Properties of logs. Okay. And would it surprise anyone that they have the same names? They have the same 3 properties. So we have the product property of logs, right? Which says this. If I have a logarithmic expression and there's multiplication inside of the log, that is the same thing as the log of the 2 separate factors added together. Right? Each separate factor will get its own log as long as you add them. What does the quotient property say? It says if you have a logarithmic expression and you have division on the inside, that is equivalent to the 2 separate logs as long as you subtract them. And finally, we have the power property of logs that says log base anything with an exponential expression. So if inside of log you have an exponent, you can sort of take this log and move them out in front. You can sort of take this log and multiply them out in front. So that exponent n gets dropped down, and then you multiply it with the log base exponential expression without the exponent. So these are the 3 properties of log. And notice the relationship is still preserved. When it comes to logs, if there's multiplication, it relates to addition. If there's division, it relates to subtraction. If there's exponentiations, it relates to multiplications. And it should make sense because we know, hey, you add the exponents when there's multiplication. Individual logs are individual exponents. So when there's multiplication, you add them. So it's sort of like a neat parallel, a neat thing to see that the properties of logs are nothing more than properties of exponents in disguise. So hopefully it doesn't take a lot to understand and memorize these, because you should already have them memorized if you know your properties of exponents. So what are some cool things you can do with these properties? Well, one thing is you can evaluate expressions that would otherwise be difficult if we didn't have a calculator or log charts handies. For example, suppose I ask you to evaluate, say, log base 4 of 2 plus log base 4 of 32. Now, it probably would not be too hard to do this without a calculator on our own because, there is some sort of relationship with 2 and 4. I think that's like a half. There is some maybe relationship between 4 and 32, but that's going to require a lot of thinking. Well, notice what's going on here. We're adding these two logs, and they have the same base. So according to the properties of logs, if logs are adding, right, you can make it as one log as long as you multiply. So because these logs are adding, I can squish them together into one log as long as I multiply them together. Now I can do regular math, right? 2 times 32 is 64. And then log base 4 is 64 should be an easier thing to answer. Of course we know that the answer is an exponent of 3. So that's one cool thing about properties of logs. It takes something that would be difficult to do by itself in pieces when it's actually easier as a whole part. Let's just do a couple more examples. Say log base 2 of 80 minus log base 2 of 5. Definitely I can't do that. That's hard to do. 5 and 2 has nothing in common. 80 and 2 have nothing in common, but let's apply the property. Notice how we're subtracting according to the properties of logs. If you're subtracting logs, you can put them together as one log as long as you divide them, divide the arguments. So this is the same thing as log base 2 of 80 over log base 2 of 80 over 5. Of course, and then you do math. 80 divided by 5 is 16, which should be easier to figure out. So that's going to be a 4. So properties of logs, hopefully, should be a nice, easy thing to figure out. Now, that is not going to be the main part of this lesson. The main part of this lesson will be to do these things called expansion and condensing, right? And as the name suggests, it's all about rewriting logs to make them bigger, more spread out, or smaller, more condensed. This is sort of like the idea of expansion. To expand, or aka break apart, a single log the idea is that every unique factor or base inside the log will get its own log. Any factor or base in the numerator will get a positive log. Any factor or base in the denominator will get a minus or a negative log. Of course, all of this would probably make a bit more sense if we did a handful of examples. So let's do an example here. Suppose I wanted to expand. Let's start off easy and then we'll work our way to the more, quote, complicated ones, which is not complicated at all. Suppose I want to expand log base 2 of 6x. The first thing I want to do is identify all the individual unique players inside of this log in the arguments. Now remember, individual pieces that are multiplying or dividing are considered a separate factor. So while most people might think, oh, 6x, that's just one piece, you have to actually treat the 6 and the x as two separate pieces because they're both separately multiplying each other. Well, according to this idea, that means the 6 will get its own log and the x will get its own log. So notice here I put the 6 and the x separate in their own separate logs. Now the idea is this: if the factors or the bases came from a numerator, the logs will be pluses, positive. If the factor or the base came from the denominator, they will be negative, minuses. I didn't have any fractions here, so these guys are all positive, pluses, because they're all both in the numerator. Yeah, that was an easy example. Let's do another one here. Suppose I wanted to expand the common log of x cubed y to the 6 over z squared. That's a little bit more interesting. So again, the first thing you want to do is identify what are the unique players, the unique factors or bases in here. Basically, every single number, every single letter should be its own unique thing. So this x is its own unique thing. This y will be its own unique thing. This z will be its own unique thing. So when I expand, the x cubed should have its own log. The y to the 6 should have its own log. The z squared should have its own log. And the idea is, if it came from the numerator, it will be a positive log. If it came from the denominator, it will be a negative or a minus log. I hope everyone can see that the x and the y came from the top, the numerator. So the log of the x and the log of the y will be positive. And the z came from the denominator, so his log will be minus. The last thing you want to do is take care of exponents. And according to the properties, if there are exponents inside of the logs, you can just move them or multiply them out in front. So the final expansion should be 3 log x plus 6 log y minus 2 log z. That is the expanded form of the original expression. Sometimes these problems, they try to be sneaky by tossing in radicals. So just have to remember, by definition, if you have a radical, that's nothing more than a fractional exponent. So don't get freaked out if they toss in some radicals here. So for example, if I ask you to, not factor, wrong class. If I ask you to expand the natural log of ab squared over 4 the cube root of c. So again, the first thing I would do is identify the unique players or factors or bases. So a, b, the 4 by itself, and then the c. We actually have 4 different players here. Again, basically you're looking for individual numbers and individual letters. So I know that when I break this guy apart, I should have 4 logs. Of the natural log of a, the natural log of b squared, the natural log of 4, the natural log of the cube root of c. Anything that came from the numerator will be positive. Anything that came from the denominator will be in minus. Notice how ab came from the numerator, so their logs will be pluses. Notice how 4 and the c came from the denominator, so their logs will be minuses. We do have a radical here, so the first thing I'm going to do is I'm going to change him to an exponent form. And according to our recollection, according to our above note here, that cube root of c should just simply be c to the 1/3 power. Now, once I have everything as exponents, you just use the exponent rule. Anything that has an exponent, just move them in front of his log. So your final expanded form is the natural log of a plus 2 natural log of b minus natural log of 4 minus 1/3 natural log of c. That is the expanded form of that example. So expansion, application of properties, every single individual factor will get its own log, figure out if it's positive or negative, bring down the exponents. Not surprisingly, we should be able to go forwards and backwards. If I can chop up a single log into individual bits, I should be able to put them back together. I should be able to condense. Now notice the steps that we took to expand. The first thing we did was give each piece its own separate log, so that's sort of like step 1. We brought down the exponents, and that's sort of step 2, and that's about it. I mean, there's only a 2-step process here. So not surprisingly, condensing will be going in the opposite direction. We're going to bring up the exponents and then squish it all together as one giant log. So I guess if you twisted my arm and you wanted to hey, Mr. Vo, write out some steps. I need steps here. So I guess this is sort of the idea of condensing, even though I don't think I need to write this because it literally is expanding in reverse. The idea is this: to condense or put together, that's what the word condense means, to put together many log expressions into one. The first thing you want to do is move, and I'll put that in quotes because we're not really moving, you're applying the property. Move any coefficients up as exponents inside the log. Right. And again, as we said before, you're going to bring everything into one log. Right. Now, how do I know what will be in the numerator and what will be in the denominator? The argument, that's the stuff inside of a log, the argument of positive logs go in the numerator. The argument of negative logs go in the denominator. Of course, all of this would make much more sense if we did some examples. Let's do an example here. Suppose I asked you to condense 3 log x plus 1/2 log x plus 1. So the first thing I want to do is take care of any coefficients. Sometimes you will have some, sometimes you won't. In this case, we do have coefficients, right? Here's this 3 in front of the log, here's this 1/2. So according to the property, these guys here get moved up as exponents. So the first thing I would do is log of x cubed plus log of x plus 1 to the 1/2 power. The moment every single log does not have a number in front of it, I don't care how simple, I don't care how ugly it looks, the next line is always the same, one giant log, right? Now you have to look at the positives and negatives of your logs. Any log that is positive, you're going to put as argument in the numerator. Any logs that is negative, you're going to put in the denominator. Now this problem was pretty boring. Everything was positive, so I won't have a fraction. So I will just put everything together. According to the property, everything's going to be timesing each other, so it's going to be x cubed, x plus 1 to the 1/2 power. There you go. Technically, you condensed it. Your final answer is one giant log. If you want to go ahead and be fancy, all right, you know that the 1/2 exponent is just the same thing as the square root. So, I mean, I will admit, this does look a little bit cleaner and nicer. Let's do another example that have like pluses and minuses just to see how things are gonna, just make things interesting. Suppose I ask you to condense 3 ln of, x plus 1/2, or let's do a minus 1/2 ln of y plus ln of z, minus 4 ln of x squared plus 1. I'm just making this up now. Whew, looks very crazy and complicated, but it really is just 2 steps. The first thing you want to do when you condense is you want to get rid of the coefficients, move them up. So I have a coefficient here. Oh, I wanted this to be a pen. There we go. Coefficient here, move them up. Coefficient, move them up. There's no coefficients, so you just leave them alone. Coefficient, you move them up. Notice I only work with the numbers. I do not touch the positive and negatives. So we have ln of x cubed minus ln of y to the 1/2 power. I'll go ahead, just to save myself some time, call that the square root of y, plus ln of z minus ln of x squared plus 1 to the 4th power. Now it looks pretty ugly still, it looks scary, but notice there isn't a visible coefficient in front of the logs anymore. The moment you don't have any coefficients when it comes to condensing, just go ahead and write one giant ln, or one giant log. Now I do see I got some pluses and minuses everywhere, so I know I will have fractions, so just draw a fraction bar. And here's the idea. Any argument that has a plus log will go on top. So notice that this x cubed, his log is positive. Notice this z here, his log is positive. So all those positive arguments will go in the numerator, x cubed z. Notice that the square root of y had a negative log. Notice the x squared plus 1 to the 4th power had a negative log. Those guys will go in the denominator. So radical y, x squared plus 1 to the 4th power. You condensed it. Looks pretty ugly, but technically it's condensed. There's only one single log. Everything is clustered together with multiplying or dividing. Okay. So that is expanding and condensing. That's 2 out of the 3 things that we need to be proficient at. That last thing we need to be proficient at is evaluating. And if you were to go ahead and look at your calculator, right? Feel free to pause the button, to pause the video if you need to look at it or find it. But most scientific calculators, non-graphing calculators, you'll see that you only have a regular log button and an ln button. You're not going to find a log base 4 button. You're not going to find a log base 13 buttons. Again, most modern calculators can bypass this. So if you do have a graphing calculator, talk to me and I'll show you. But for the basic scientific calculators, you're only going to have a common log and a natural log. Well, what if I wanted to figure out log base 5? What if I want to figure out log base 4? Well, we have this thing called a change of base formula. Now, if you're interested in knowing where this formula comes from, please talk to me. It's pure algebra, but for the sake of time, I'm not going to show the derivation. But if you are interested, I will totally show you in class. It's pretty simple and fun. But the change of base formula says this. If you have a logarithmic expression, log base b of something, that is equal to log base c of the original argument over log base c of the original base. And here's the idea. You get to pick what that c is. Well, if we get to pick what that c is, and our calculators can only do common log, base 10, or the natural log, base e, it sort of makes sense that might as well make c 10 or e, because then we can use our calculators for it. What this says is, if I had something like, for example, log base 407. All right, there's no way we can do this mentally without log charts, because 7 is not a nice power of 4. What this change of base formula says here, that is equal to log base whatever of 7 divided by log base whatever of 4, right? And again, we can put whatever we want in these boxes. So if we wanted to, it'd be pretty stupid, but if we wanted to, we can put a 5 in the boxes there. Or heck, I can put a 13 in those boxes there. Or heck, I can put in, let's do fractions, 1/2 in there. Why not? It's stupid. It doesn't help me solve it, but we could do it if we wanted to. Well, the smart thing to do is just to use a common log or an ln, because these guys here, we can use your calculators for. So that's the change of base formula. It's just a nice, easy way of using your calculator to calculate, quote, hard logarithmic expressions if your calculator does not have a log base b button. Again, most modern day scientific graphing calculators do have it, and if you want me to show you, just ask. So there you go. That is, what is this, 4-4.